Hello everyone, my name is David Justo, and today I want to tell you about a little framework that makes it possible to factorize machine learning algorithms across multiple programming languages. This is joint work with my peers Shaoqing, Lukas Stadler, Nadia Polikarpova, and Arun Kumar. So today we live in a polyglot data science world, where data scientists utilize different languages and tools at different stages of their workflows. This means that it's not unusual to see data that was cleaned in R be later repurposed for training models in Python. And similarly, production-ready models trained in Python are often loaded and deployed on top of JavaScript. And so in this polyglot data science world, we have strong incentives to make our data science tooling available in as many programming languages as possible. But developing systems that work across multiple languages is no easy task. For an example, let me tell you a little bit about Morpheus. Morpheus is a factorized ML framework, which means that it allows off-the-shelf ML algorithms to work directly over normalized relational datasets. For context, the act of denormalizing data through joins often introduces redundancy to the resulting matrix, which leads to model training inefficiencies. Instead, the Morpheus rewrite rules push linear algebra operators through the joins of normalized relational datasets, and it allows them to work directly over the base tables, leading to faster training times. And I tell you all of this because Morpheus was originally written for R, but we wanted to make it available in several languages. However, we quickly realized that this would bring about a massive development challenge for us. You see, on one end, to support a new language, we would need to re-implement each and every Morpheus optimization, which is easier said than done, as our experience re-implementing Morpheus in NumPy taught us that in order to get good performance, you need to combine these rewrite rules with domain knowledge about the language we're aiming to support, and that just takes time to acquire. And on the other hand, as we come up with new optimizations, having a growing list of supported programming languages means that now there's work to be replicated across each language. And so this was shaping up to be a massive development burden for our research team. And at the core of this challenge is an issue of duplication of effort. We needed to find a way to disentangle the symbolic specification of Morpheus rewrite rules from the fine-tuning, optimizations, and domain knowledge needed to properly support a new language. We developed Trinity to address this very problem. Trinity is a framework that supports the development of Morpheus-style, multi-language, factorized machine learning with ease. Our core contributions are the following. First, to our knowledge, this is the first system to study the generalization of factorized machine learning to multiple languages at once. Second, in building on top of the GraalVM platform, and we'll get to that shortly, we developed new interoperability abstractions for GraalVM that facilitate interoperability with matrix data types. Finally, using Trinity, we quickly developed 3 new lightweight implementations of Morpheus, one for R, one for JavaScript, and one for Python. So how does Trinity work? Well, the first thing you need to know is that it's built on top of GraalVM, a language runtime that supports R, Python, JavaScript, and several other languages. For us, the main benefit of using GraalVM is that it provides us with high-level interoperability tooling that will allow us to communicate across programming languages. And so with that in mind, Trinity is made out of 3 core components. The first is the normalized matrix. A normalized matrix is an abstraction in the Morpheus literature that holds the base tables of a normalized relational dataset but exports the interface of a single matrix. And so when a linear algebra operator is invoked in this abstraction, a Morpheus rewrite rule will trigger to perform the computation over the normalized data within. And that leads us to our second component, the rewrite rules. The rewrite rules are specified in a new GraalVM language that we call MorpheusDSL. And third, these MorpheusDSL rewrites are powered by Matrixlib, an interoperability abstraction that we developed to encapsulate all domain-specific knowledge needed to properly embed the rewrites in a new language. Now let's dive deeper into each of these components, starting with MorpheusDSL. MorpheusDSL is a GraalVM language whose ASD node semantics correspond to Morpheus rewrite rules. Here's how it works. Say we're multiplying a normalized matrix with 5. In yellow, we have the ASD nodes of a language like R, and in blue, we have the multiplication operator of MorpheusDSL. At runtime, the MorpheusDSL node expands to several calls back to R's own linear algebra libraries, which perform the actual computations. And this is possible because GraalVM's interoperability features allow users to execute code across multiple languages. But how do these rewrites work regardless of language? Well, that's where Matrixlib comes into play. Matrixlib is a unified matrix interoperability abstraction for GraalVM. In essence, it defines a collection of generic method signatures that should be callable from any matrix data type. And so using this abstraction, MorpheusDSL can define a rewrite rule in terms of these generic matrix operators and have them work regardless of the programming language that it is interacting with. This works by leveraging the adapter pattern. So we have adapters in every supported language to translate from the Matrixlib interface to that language's own linear algebra procedures. The adapters serve not just to perform a simple interface translation, they also host language-aware optimizations and other domain knowledge which, as we already mentioned, is crucial towards achieving good performance. For instance, an adapter might implement the matrix multiplication operation for NumPy in different ways, depending on whether the target is a sparse or a dense matrix. With MorpheusDSL and Matrixlib out of the way, I think we're ready to revisit our architectural diagram. So let's review. We're given a normalized relational dataset and we want to train some machine learning model over it. Instead of materializing a join, we can construct a normalized matrix, an abstraction that wraps over the dataset's base matrices but exposes the interface of a single matrix. Now, we can feed in the normalized matrix to some machine learning algorithm as the input. And when the algorithm wants to perform a linear algebra operation over this abstraction, GraalVM's interoperability features allow us to invoke the corresponding rewrite rule from MorpheusDSL. MorpheusDSL then generically rewrites the operation to work over the base matrices using Matrixlib. Finally, Matrixlib adapters then further optimize the rewrite rules using programming language-aware domain knowledge that optimize each operation further. And there you have it, the flow of a simple rewrite rule with Trinity. In the paper, we explain how to augment this workflow to optimize a Polyglot script. For example, Trinity can factorize an algorithm written in Python that learns over a dataset represented in R. See the paper for details. Finally, let's talk about Trinity's performance when factorizing two algorithms, logistic regression and k-means clustering. In doing so, we can compare Trinity against two other execution modes. The first, against a pre-existing but single language Morpheus implementation, and the second, against the materialized approach, that is, training the model with a de-normalized dataset. For time, we'll set the comparison language to be R, and we'll show results when trained over a real-world 3-table dataset of movie reviews. In the paper, we also include benchmarks for Python and JavaScript, use a total of 7 real-world datasets, and factorize 4 distinct machine learning algorithms. See the paper for details. Starting with the logistic regression results, we see the materialized approach takes about 165 seconds to complete, but both Trinity and Morpheus perform about 8 times faster than that. And things are not too different in the k-means case. Here, the materialized approach requires around 358 seconds to train, but both Trinity and Morpheus reduce this time by about a factor of 5. And these trends continue across datasets and models. What we see is that Trinity achieves speedups comparable to that of a single language Morpheus implementation, although the single language approach does seem to have a slight performance advantage. However, in our experience, the relative difference between a single language Morpheus implementation and Trinity never exceeds 20%, and is often much smaller. It's a big win, especially considering that Trinity leverages a more generic implementation. In this presentation, we've introduced Trinity, a polyglot framework for factorized machine learning. Trinity leverages cutting-edge interoperability tooling to factorize ML algorithms across multiple programming languages. It solves a developability challenge in trying to make a framework available for multiple languages, and it does so without sacrificing performance. You can find out more in our project page, which includes the code and the paper, by following the link that's up in the slides. Finally, we thank Oracle and Google for their support in this work, and we thank you for your time. Thank you.